The Winkler method, a three-step experimental technique used to determine the amount of dissolved oxygen in water. Each step, an oxidation-reduction reaction. Now I'm going to show you the three equations that we'll be using. You do not need to write these down, but you do need to be able to use them. The first reaction, you have manganese that's being oxidized and oxygen that's being reduced. In the second one, manganese is being reduced and the iodide ion will be oxidized into elemental iodine. And then the last one, sulfur is being oxidized and elemental iodine is being reduced. Now let's take a look at exactly what's going on here. Again, you do not need to know, for this slide, just listen. You don't need to copy this down, but it's good to have a sense of what's going on here for the calculations that we'll be doing. So an overview, steps. Manganese 2 sulfate and lithium hydroxide are added to a sample of water that is being analyzed. Any dissolved oxygen in the water will react to form manganese 4 oxide. And so this reaction is one of those redox reactions that takes place in basic solution. Remember, we've done it in acidic solution, but this particular reaction needs to be in basic solution. So any oxygen, O2, that is dissolved in the water, and that's why it's written aqueous, because it's the oxygen gas dissolved in water, so AQ. Any oxygen that's in the water will undergo a reaction with the manganese in basic conditions, and it'll form the manganese 4 oxide. The next step, potassium iodide and sulfuric acid is then added to produce elemental iodine. So the manganese 4 oxide that was produced is now going to undergo a reaction with iodide, and it's in acidic solution. So this is a redox reaction that takes place in acidic solution. Now this will produce elemental iodine. And then the third step, to determine the amount of iodine that's produced, the solution is titrated with sodium thiosulfate using starch as an indicator. So the indicator will change color. And that will enable us to determine how much iodine we have. Now, it's a little confusing here, but what we're going to do, we're going to go backwards to once we know the amount of the titrant, the sodium thiosulfate, which is the thiosulfate here, how much of that we need to react with the iodine tells us how much iodine we had, which tells us how much manganese 4 oxide we had, which tells us ultimately how much oxygen we had. Okay, you do not need to copy this down either, this slide. Now, I've given you the 3 steps again, and I've boxed the particular reactants and products that are of particular interest. Now, the Winkler method is an experimental process. The last step is when you titrate sodium thiosulfate into your sample of prepared water. The water was prepared by steps 1 and 2 that I just walked you through. So the water is all ready for the last step, to add the sodium thiosulfate. Now also that's been added is starch, which is an indicator that it'll change color once this reaction has gone to completion. So the starting point is titrating, or the last step is titrating the water with the sodium thiosulfate. And once you get to the end point, when the starch changes color, then that will tell you the amount of iodine that you had, which will tell you the amount of manganese 4 oxide that you had, which will tell you ultimately the amount of oxygen that you had in your water sample. Now the amount of oxygen that you had in your water sample, we're going to be measuring that in a unit called parts per million, and it's exactly like it sounds. If you had 1,000,000 molecules of water, and within that 1,000,000 molecules of water you had 1 molecule of oxygen, well then it would be 1 parts per million. Okay, I'm going to show you a video. Richard Thornley from the IB Chemistry video review tutorials. He's going to show you the Winkler process in its entirety. Pretty cool.
This is water from the East River of New York. So I'm going to put it into this container. Now you need to have a known volume of water Now this is a 250 milliliter volumetric flask, but I'm actually going to fill it up completely. It's going to be slightly more than 250, and I'm going to have to work that out later. I don't want to leave any air in the flask because, of course, then I'll be measuring the oxygen from the air and the water. I just want to measure it from the water. So I'm absolutely going to fill this up, even overfill it. Let me take the temperature. A chilly 8 degrees. Okay, now I've knocked a bit of the water out. Okay, grab some manganese sulfate monohydrate. This supplies the manganese 2 ions. I've worked out you don't need much. Oh, you need some though. There we go, smashing. About that much. You put that in. And strangely enough, one of these pillows, an alkaline iodide azide pillow. So this supplies iodide and increases the pH because we need those hydroxide ions. Ooh. Cut that off. Goggles on. Okay, a bit of a second too late. Let's try and pour that in as well. That looks weird. Cork it up, making sure there's no air bubbles. And shake it, baby. Now, if it turns brown, that means there is some dissolved oxygen. And indeed, it is turning brown. It's quite hard to shake it because there's no air pocket to shake the liquid into. The brown is the manganese 2 turning to manganese 4. Ooh. Okay. Set it down, and you've got to let the precipitate settle out about halfway. And once the flocculant or the precipitate has settled out about halfway, shake it up again. And then wait again for the flocculant to settle about halfway. Okay, so still no air bubbles, seems quite good. We had the manganese 4 ions here, which is kind of the brown manky colour. Now I have to reduce the pH for the next part to work. Carefully remove the stopper. And I'm going to add 2 milliliters of concentrated sulfuric acid. Move back a bit in case I spill it. That was just under 2. So this is an excess, doesn't have to be exact. Alrighty, and you can see the reaction taking place here. The new brown colour is iodine molecules being formed all the way through. And the kind of cloudy manganese 4 has turned into manganese 2. Okay, now transfer your solution, because we can't really do a titration. Oh, and you know what? It's pretty stable, but you don't want to aerate it any more than you have to. Although the number shouldn't change, because these chemicals you've added have stabilized the oxygen level. And no reason to tempt fate. Alright, now we're going to do a titration. This is sodium thiosulfate. Now, if I wasn't so brave, I'd split this sample in 2 to give me 2 tries at doing it. But let's see if I can titrate first time. Sodium thiosulfate is going to turn the brown I2 iodine molecules into colourless iodide molecules. The transition from brown to not brown isn't as obvious as you'd like. So When I get close to the end, I'm going to add a little starch, and that's going to sharpen the end point. Add a little starch, non-toxic, literally a pinch. Literally 2 pinches. Okay, so the end point is now sharpened. It's hopefully going to be 1 drop, changes everything. Now that might be the end, I can't tell, so I'm going to take a reading. It's exactly 1.95 milliliters. So I'm not sure if that's the end. So I'm going to remember 1.95 milliliters. Oh, you probably should write it down if you're doing the experiment. Now let's carry on and see if this is indeed the end. Seems to be getting more colourless. Let's see if that's the end. I'm writing down in my brain 2.7 milliliters. 2.7 milliliters. Ah, you know what? It wasn't an instantaneous reaction. I think we're pretty much done.
Okay, so these are the 3 equations. You won't be asked to remember them, but you'll be asked to use them. So if I know the concentration of the sodium thiosulfate, and I know the volume of sodium thiosulfate I've used in my burette, I know the moles. If I know the moles, I can work out the moles of iodine, which is the same as the moles of iodine there. And if I know the moles of iodine there, I can work out the moles of manganese 4 oxide, which will be the same as the moles of manganese 4 oxide there. And once I know that, I can use that to work out the dissolved oxygen content. Now, if I know the moles of dissolved oxygen, and I know the volume of water that I used, I can work out the concentration. And so that's a broad overview of the theory.
Okay, you will want to take notes on the rest that I have to offer here. Biological oxygen demand, BOD. The Winkler method can be used to measure the level of organic pollution in water. Specifically, biological oxygen demand is the amount of oxygen in parts per million needed by bacteria to decompose organic matter aerobically, that is, requiring oxygen, in a fixed volume of water over a set period of time, usually 5 days. So we calculate the biological oxygen demand by taking the amount of oxygen that we had in the water initially and then wait 5 days and then determine the amount again. Now, if they're exactly the same amount, then we're good. Nothing's in the water that consumed the oxygen. There's no bacteria in the water. But if the amount of oxygen goes down dramatically over 5 days, well, we want to stay away from that water because there's something living in there. The higher the biological oxygen demand, the more impure the water. And just here's a few examples. Pure water, we'd want it to be less than 1. Domestic sewage, around 350 parts per million. Slaughterhouse wastewater, my favorite, about 3,000 parts per million. So really disgusting stuff. Dissolved oxygen. The oxygen molecule is quite nonpolar and has a low solubility in water, about 9 parts per million at 20 degrees Celsius. The warmer the water would be, the less soluble the oxygen would be, the less soluble any gas would be. Now, oxygen is very nonpolar, but of course, water is very polar. If you've learned nothing else in my class, please remember that water is a very polar molecule. That's why it has such unique properties. Okay, I'm going to show you this little video clip here to explain why a nonpolar molecule like oxygen would dissolve in water.
On average, the electron cloud of an O2 molecule is distributed symmetrically across the molecule. The molecule is not polar. A water molecule, which is polar, repels the electron cloud, causing it to be asymmetrically distributed and thereby induces a dipole in the O2. This shift allows O2 to be weakly attracted to the water molecule.
Fast-flowing rivers and streams are usually not polluted as their water is continuously exposed to air where reoxygenation can occur. However, static bodies of water such as lakes and ponds have limited reoxygenation and are prone to biological pollution. So you have things that start growing in the water. And just FYI, the lowest concentration of oxygen that fish need to survive is about 3 parts per million. All right, let's do a practice problem. A 200 milliliter sample of water was analyzed using the Winkler method to determine its biological oxygen demand. Initially, the water had an oxygen content of 12.3 parts per million. After 5 days, it took 10.5 milliliters of 0.0100 molar sodium thiosulfate to react with all the elemental iodine that had been produced. Calculate the oxygen content in the sample and its biological oxygen demand. Okay, so there's a lot there. Let's unpack it. So summary, this will be from all of that. This is what you need. You need to know that you had a 200 milliliter sample of water, and we can convert that to liters right now, so 0.2000 liters. Okay, we need to know the initial oxygen content, which was 12.3 parts per million. And then, after 5 days, it took 10.5 milliliters of the 0.0100 molar sodium thiosulfate. So the amount of titrant, the sodium thiosulfate. So we need to know its volume and its concentration. Now the sodium is a spectator ion, so we'll be ignoring that and treating it as if it's just the thiosulfate. Okay, let's get into a calculation. So these are the 3 equations that we'll be using, and we'll always start with the volume of the titrant that we used. And so we used 10.5 milliliters. First thing we want to do is convert that to liters, and we want to do that because we're going to now multiply it by the concentration. Remember, the concentration was 0.01 molar, and that's moles per liter. And so we now, if we were to stop here, we would know the number of moles of the thiosulfate that we used at this point. Okay, so now I'm going to use step 3, the mole ratio from step 3. And the mole ratio tells us for every 1 mole of iodine that reacted, we needed 2 moles of the thiosulfate. So the 2 moles of thiosulfate go in the denominator. And so at this point, if we were to stop, we would calculate the amount of iodine that we have at this point. Then I'm going to jump up to step 2. And the mole ratio here is 1 mole of elemental iodine for every 1 mole of manganese 4 oxide. So it's a 1-to-1 mole ratio. The moles of iodine go in the denominator, so they cancel out, and that gives us the amount of the manganese 4 oxide. Then I'm going to jump up again to the next equation, and we'll be looking at the mole ratio between the manganese 4 oxide and the oxygen. So in step 1, it's a 1-to-2 mole ratio, 1 mole of oxygen for every 2 moles of manganese 4 oxide. The manganese 4 oxide cancels out, and that would give us the number of moles of oxygen. Now we're interested in calculating the amount of oxygen in parts per million, and that's most easily done by converting the oxygen to grams. And so I'm going to convert the oxygen to grams. There's, in 1 mole of oxygen, it's 32.00 grams. And that gives us a total mass of oxygen in our 200 milliliter sample of 0.000840 grams. Now remember that that came from our sample of water. So I'm going to divide that mass by the volume of water, of our water sample. And so we have that many grams of oxygen per that volume of water. Now for a reason I'll explain in a second, I'm going to convert grams into milligrams. There's 1,000 milligrams in a gram. And that would give us 4.20 milligrams of oxygen per liter. And the reason that we wanted milligrams is, as it turns out, 1 milligram per liter of water is 1 part per million. There are 1,000,000 milligrams of water in a liter. There's 1,000 grams in a liter, 1,000 milligrams in a gram, 1,000 times 1,000 is 1,000,000. So in a liter of water, there is 1,000,000 milligrams. Now you don't need to worry about that. Just remember that you're interested in calculating milligrams of oxygen and dividing it by the volume of your sample. And that will give you the same number as parts per million. So 4.20 parts per million. Now remember, that is not the biological oxygen demand. That is the amount of oxygen after 5 days. We need to do one more step to calculate the biological oxygen demand. But it's an easy step. Now remember, to calculate the biological oxygen demand, all we need to do is to subtract the amount of oxygen that we have after 5 days from the initial amount. And the initial amount was given in the problem itself. So initially we had 12.3 parts per million, and now we just calculated we have 4.20 parts per million. So that means that the biological oxygen demand was 8.1 parts per million, which means there was something living in the water to consume the oxygen. Now, it doesn't matter, I should point out, it doesn't matter what the amount of oxygen is. You can just take a straw and blow bubbles into a glass of water and oxygenate it, increase the amount of oxygen that you have in the water. What's important is the amount of oxygen that is consumed after a certain amount of time. So biological oxygen demand, the amount of oxygen that was consumed. So 8.1, probably not so good. Would you drink this water? Well, if we use this scale here, we see that 8.1 is down here. So it's poor, somewhat polluted, usually indicates organic matter is present and bacteria are decomposing this waste. So probably wouldn't want to drink that water. All right, so that is how we use the Winkler method to calculate the biological oxygen demand for a sample of water. And that's what you'll be asked to do on the test, one of these problems. But for now, that is the end of notes.